Let's spend a few minutes now talking about numpy. Numpy is arguably a very, very powerful, and we'll be using lots of that in the coming weeks, mechanism for representing data and doing a lot of different manipulations. Primarily what we will use it for is linear algebra. Built into your build of Python is almost certainly is numpy, but if it's not, go ahead and install it. And I'm going to import numpy as np. That way I don't have to write numpy in front of every command that we're going to use. So you can think of numpy in its simplest form as simply another way of representing arrays and matrices and multi-dimensional lists. That's a gross simplification, but for now that's what I need you to think about, and then we'll see some of the other power of numpy as we move forward. So I'm going to define, let me go ahead and just evaluate this so we can see it, a numpy array from 0 to 1 in steps of 0.01. So the arange function will generate a list for you with the value starting at 0 and up to this value non-inclusive in steps of this. So I got 0, 0.01, 0.02, and so on and so forth. And so when I just type t, I can see that. And you can see it looks a lot like a standard list, but it has this array thing here, which tells us that this is a numpy object, not a standard list. There's going to be good reasons why we want to use numpy list versus list, and I'll show you that in a few minutes. Now, one of the nice things of the numpy, excuse me, is we can do some very simple operations on arrays without a lot of fuss. So for example here, I have specified the same numpy range, 0 to 1, in steps of 0.01. And what I'm plotting here is, let's see, here's the x-coordinate, here's the y-coordinate, and I'm plotting something in red, and here's my show. So we just described plot in the previous segment. So 2 times np.pi, so of course pi is the 3.14, that is built into the numpy library, times t. So let's just think about this command here for a second. So 2 is a scalar value, pi is a scalar value, but t is an array. But look at what you can do. You can treat arrays as if they are scalar values. So when I multiply a scalar value times t, it takes each element of that array and multiplies it by 2 times pi. So I don't have to loop through that array, for example, multiplying each element by t. This is a very MATLAB-like structure as well. And so now I've taken t and I've multiplied it by 0 times 2 pi. Why did I do that? Well, because now this axis is not 0 to 1, but it's 0 to 2 pi, 6 point whatever. And I'm going to plot against that the sign, so np.sign, sign being the sinusoid function within the numpy library, of 2 times pi times t. So I'm just getting a sine wave. Okay? And so notice here that the important take-home message here is that you can take an array, a multitude of values, and multiply them by a single scalar value, and it simply multiplies every element of that array by that scalar value. And that's just sort of nice, convenient notation, so you don't have to worry about things like for loops to do all of that. Okay. So one of the nice things that you can do in these plots is you can start to make them actually look pretty nice. So I've got my a range here, the same as before, my numpy range. I'm plotting 2 pi times the sine of 2 pi, and here I've done a little bit of annotation. So plot.annotate says, please put in the text 0 crossing, you see it right there, at position pi 0. So let's see, pi is here and 0 is here. And so that's going to annotate starting at this point. And then I'm going to put text at position 0.5. And then the arrow connects those two. So it connects this XY position where I put the text. So it's as if I'm pointing to a point. What point? What the XY parameter says. I put the text at some point, and then it just draws an arrow between those, and I can specify what the color is. So it's a nice way when you're doing data visualizations, you can point to certain things and annotate them programmatically. And that's always nice because if these values change because they are determined because of your data analysis, you're not shoving these things into some photo editing software and then having to change them over and over again. It's all done programmatically. And here I've just placed a grid on so I can actually see how the horizontal and the vertical axis line up. Okay, a couple more things to look at, also in the realm of both numpy and the plotting. I'm going to define a function here. So of course I'm importing matplotlib and numpy as before. I'm going to define a function that takes as input as you will see in a minute, a numpy array, and it returns a damped sinusoid. I'll explain that in a second. So I'm going to again define my array to be 0 to 4 this time in steps of 0.01, and I'm going to plot t versus decay of t. I'm going to x label time, y label energy, so that puts time here, energy here, and a title here. So this is a nice way of annotating your plots. And of course, at the end, I'm going to show it. The function here is one of my favorite functions. It is a so-called damped sinusoid. So this part you can see is just a cosine, same as a sinusoid, but phase shifted by 90 degrees. So it's just np times cosine 2 pi times t. So it's 2 pi times this. So it's multiple cycles of a sinusoid. And then I'm going to multiply that by a exponential to the minus power t. So what does that look like? That looks like something that decays going downwards. Okay? So e to the 0 is 1. E to any negative value is going to be less than 1. And so I take a sinusoid that looks like this, and I damp it by an exponential that looks like this, and I get a so-called damped sinusoid, where the oscillations are damping over time. Notice again here, I can multiply a numpy array by a scalar value. It multiplies every element by that value. But I can also multiply two arrays. So this is an array. It's the cosine of all the values in t. This is an array. It is the exponential of all the values in the array. And when I multiply them, by default what it does is it point-wise multiplies. So think about it as lining up the two arrays and multiplying all of the values, and then that gets returned. So again, very convenient mechanism for manipulating these arrays in terms of point-wise multiplication, point-wise addition, and scalar multiplication or scalar addition. Lastly, just one more command I want you to be aware of, which is the histogram command inside of matplotlib. So here I've generated in numpy, so I've again imported numpy and matplotlib. I'm tapping into the random library event numpy, and I'm generating 100,000 normally distributed random numbers. So rand n stands for random normal. Normally distributed means there's zero mean with unit variance with a bell-like or Gaussian distribution. And I can, for example, plot a histogram of those values with 20 bins, and you can see that nice normal distribution as we expected. Okay, so again, lots of things we can talk about in NumPy, lots of things we can talk about matplotlib. This is the basics of what you're going to need to do some of the assignments coming forward. But obviously, as you do more and more Python programming, certainly NumPy and some graphics routine you're going to get more comfortable with and more familiar with over time. All right, when we come back, there's two more things we're going to do. We're going to do one drill, so please carve out a little bit of time to do the drill. And when we're done with the drill, I'm going to talk a little bit about images within Python, because we're going to do a bunch of exercises in the coming weeks using digital images. See you in a few minutes.